Hello and welcome. Today we will learn about enzyme mode of action. What do laundry detergents, cheese, and your own saliva have in common? They all contain powerful enzymes. We use them in our daily lives, but how do they actually work? What does it mean when we say an enzyme catalyzes a reaction? Stick with me. Let's do a quick thought experiment. Imagine dropping a sugar cube into a glass of water and just waiting for it to dissolve on its own. It would take a frustratingly long time. But the moment you stir it with a spoon, the cube vanishes almost instantly. The spoon is a catalyst. It makes the reaction fast and efficient without being used up itself. This is exactly what an enzyme does in your body. It's a biological catalyst that dramatically speeds up essential chemical reactions, making life possible. Every enzyme has a special region called the active site. Its unique shape means it only fits one, or a few, specific partner molecules, called substrates. This is called specificity. When we talk about binding energy, it is the energy released when the enzyme binds the substrate. The bonds are non-covalent bonds, which are hydrogen bonds, van der Waals forces, and ionic interactions. Let's talk about the enzyme function as a cycle. An enzyme binds its substrate, forming an enzyme-substrate complex. Inside this temporary complex, the substrate is transformed into a new product, creating an enzyme product complex. Finally, the product is released, and the enzyme is recycled, ready to bind its next substrate. Here comes the cofactors and coenzymes. The enzyme sidekicks. Think of an enzyme's protein part, the apoenzyme, as an incomplete tool. It's powerful but needs a helper. This helper is called a prosthetic group, which can be a cofactor, an inorganic ion like magnesium or iron, or a coenzyme, which is an organic molecule like acetyl coenzyme A. When the apoenzyme binds with its prosthetic group, they form the active, complete enzyme, known as the holoenzyme, ready to catalyze. Let's go back to our sugar cube in the glass of water. The glass, water, and sugar cube together, that's our substrate. The spoon is enzyme. The hand is the cofactor or coenzyme. Without it the enzyme is useless, but together, they make the reaction happen. Let's talk about the activation energy curve. A chemical reaction is like pushing a boulder over a steep hill. That hill is the activation energy. Without an enzyme, that hill is difficult to climb. The enzyme works by providing an alternative pathway, which makes the hill much smaller and easier to cross. At the very top of this hill is the transition state, a fleeting, high-energy moment. The unaffected energy by the enzyme is delta G. How enzymes lower that activation energy and make the climb easier? 1. Orienting substrates correctly. 2. Covalent bond between enzyme and substrate. 3. Providing a stable intermediate or transition state. 4. General acid-base catalyses. 5. Metal ion catalyses. Keep in mind that enzymes change activation energy but not energy of reactants or products. As an example, a group of frogs need to jump from one pond to another. But between them is a tall wall of rocks, the activation energy barrier. Most frogs can't muster the energy to clear it. Now, introduce an enzyme. It doesn't move the ponds, but it lowers that rock wall. The barrier is now so low that the frogs can easily hop across to become products on the other side. The reaction is complete. When we talk about the lock and key model, it describes enzyme specificity. The enzyme's active site is a rigid lock, and the substrate is a precise key. Only the correctly shaped substrate fits perfectly to form a complex. In the induced fit model, the hand, which is substrate, meets a flexible sponge, that's the enzyme. Upon contact, the sponge dynamically changes its shape, conforming perfectly around the hand. This mutual adjustment occurs in induced fit. The enzyme's active site is reshaped by the substrate, leading to a precise fit that activates the catalytic process. Lactose tolerance and intolerance are a perfect demonstration of what happens when an enzyme is present or missing. In a lactose-tolerant person, their body produces the lactase enzyme. This enzyme actively breaks down the lactose sugar into glucose and galactose. However, in a lactose-intolerant person, the body produces very little or no lactase enzyme after infancy. Without this specific molecular machine, the lactose sugar remains intact and undigested. There, gut bacteria ferment it, leading to symptoms of discomfort. Hope you understood how enzymes work. Thank you for watching.